So welcome back to the analysis seminar. Our speaker today is Marina Iliopoulou from Kent University, and her title is Sharp LP Estimates for Oscillatory Integral Operators of Arbitrary Signature.
Okay, thank you very much, and thank you for inviting me to speak here. This is joint work with Jonathan Hickman, and the motivation comes from the Fourier restriction conjecture in harmonic analysis. So this conjecture says, let's take a surface of non-vanishing Gaussian curvature. So the principal curvatures everywhere are all non-zero. And let's take any function defined on the surface or a compact patch of the surface and take its Fourier transform. What does the Fourier transform look like? And usually here it's comfortable to define the function on a lower dimensional space, Rn-1. So the function will be defined on the unit ball in Rn-1, but you can think of it as lifted on the surface, if you like. And to calculate the extension operator, as we call it, this type of Fourier transform at any x in Rn, we take the integral of this function f, but we integrate against the twist, which has to do with a point x. So mainly we're inner producting x with anything on our surface. What we know is that this Fourier transform, the extension operator, is arranged in wave packets, as they're called. So more precisely, if we take any little cap on the domain of f, then we can look at the Fourier transform from that cap only. And in fact, there is a cap that lives right above this on the surface with a specific normal that depends on the surface. Well, the Fourier transform is arranged in tubes. They're quite fat and parallel to each other and all point in the same direction. That's the direction of that normal. If you take another cap, say a blue one here on the domain, then above it we have another normal because of the curvature, and we have that the Fourier transform from that cap is arranged in parallel tubes pointing in that other normal. And the conjecture says that in principle, when these waves interfere, because the tubes carrying them meet, this interference is in fact, in principle, destructive. So the waves cancel each other out a lot. So much that we expect that the p-norm of the extension operator is controlled by the p-norm of the original function for a wide range of exponents, so almost as low as 2. Even though the original function is defined on a lower dimensional space on the Fourier transform. And here, I should say it's easier to localize the extension operator inside the big ball of radius r. And there we're aiming for such an estimate. So the LP norm on this big ball is controlled by the P norm of the original function, even at the endpoint, but with a potential loss depending on the radius. Right, so what we're proving, part of what we're proving is improved restriction estimates when the surface is a hyperbolic paraboloid. So here is one of the results. We are taking any surface of non-vanishing Gaussian curvature, just like the restriction problem says. And we're looking at the difference between the positive curvatures and the negative curvatures, principal curvatures at any point. That is the signature of the surface. And for such surfaces, we provide improved restriction estimates as long as sigma is not minimal or maximal. So let's see an example. Classic examples are hyperbolic paraboloids, where you see a quadratic form here, and the number of pluses is the number of positive curvatures, and the number of minuses is the number of negative curvatures. So the extremal situations that we don't improve on are, first of all, the case of maximal signature, where you only get pluses, essentially. So that's as large as the signature can get, is n-1, and that's the paraboloid. And the other extreme is a saddle. So that's when we have minimal signature. Mainly, the ideal scenario is when each positive curvature cancels out a negative one. So in total, the signature is 0. Of course, that's possible only if the omega variables are even in total. If the omega variables are odd in total, then we can have cancellation of the curvatures plus minus 1 by 1, but 1 will remain in the end. So the minimal signature in that case is 1. So these are the cases that we don't treat. But in every other case, we have the LP estimates for the extension operator that we said earlier. And here are the lowest exponents for which we prove them. So these exponents depend on whether the signature is even or odd. So for even signature, this is the exponent we prove. For odd signature, this is the one. But okay, as I said, the extremal cases were solved before. The minimal signature case was treated by Stein and then by Bourgain and Guth. And the maximal signature case was done essentially by Guth for the paraboloid. And then we worked on general surfaces with him later. Of course, this is sort of not natural, okay? The restriction problem says that no matter what signature the surface has, we should have the same LP boundedness properties for the extension operator. So it's sort of unnatural to split the problems according to the signature. But there is a reason for this, and the reason is that we were actually interested in a more general problem than the restriction problem, and that has to do a lot with the signature. So this theorem is a byproduct of that. And let's see what that problem is. Remember, this is the restriction conjecture we talked about. And the point about it is that when you take this Fourier transform at any x, every time you're integrating against this fixed surface, sigma. So Hermander asked, what happens if instead of integrating always against this fixed surface, you integrate this against a surface that depends on x, like this? So if you calculate the new Fourier transform at x, you integrate against sigma x. And then if you calculate at an x prime that's close to x, you integrate against another surface, sigma x prime. So this is a variable coefficient scenario. The surface should smoothly change with x, roughly speaking. And Hermander also said we should think of these surfaces as always having non-vanishing Gaussian curvature. If that's the case, what are the LP bounds that we can take for this operator? The scenario is sort of similar to the restriction problem. So if you look at these two caps that I drew earlier on the domain of F, from the red cap, above it now, we have many different normals because the surfaces are changing. So the red cap gives rise to curved tubes that carry the waves. And the blue cap, again, above it, we have many different normals as the surface changes. So we also have curved tubes coming out of it. But still, we do have a wave packet decomposition. And Hermander asked, does the same restriction conjecture hold for this problem, for this variant? So can we still have, do we still have that this operator is bounded from LP to LP for the same range of P as for the extension operator? I said that I wasn't precise when I defined the Hermander operator here. So let's just be a bit more precise to see what we mean. Here is a dictionary that takes me from the extension operator to the Hermander one. So here's the extension operator. The point is we want to change the phase function here, this inner product, into something much more general. And it's a bit of a tedious process, but here it is. Let's take the arbitrary x. As we said, we have localized in a big ball. We don't like to say that all the time. So we take a cutoff function that tells us that the x variable is on a unit ball in Rn, and the omega variable is in the unit ball in Rn minus 1, where f is defined. And we simply adapt our variable x so that this is non-zero only in a ball of radius r. So we divide x by r. And we change the phase function so that this x over r appears. We multiply and divide by r. And here is this phase we have. if phi is the inner product of a fixed x with our surface, where x lives in the unit ball, once we adapt to the ball of radius r, we are dividing x with r inside phi, and we're multiplying outside with r. Okay, so we call this quantity phi to the power r, and that's the phase we have here. Now the Hermander operator comes by essentially replacing this specific phase function with a general phi r, where the phi r is defined pretty much the same way as before, but for a general phi, a smooth phi. So while before the smooth phi was an inner product of something with a fixed surface, now it's just a general smooth function. And the cutoff is just like before, because we want to localize in a big ball of radius r. The thing is, okay, we can't expect nice LP boundedness properties if phi r is anything at all. We want it to resemble a bit the phase function of the extension operator. And we said that we want to think of it as the inner product of x with a variable surface. So let's see in the extension operator case how the surface is connected to the phase. You notice that if you take the phase and you integrate it with you differentiate it with respect to x, you recover the surface against which you're integrating. So that's what we do in the Hermander situation. We just differentiate our phase with respect to x, and we get something that we think of as this variable surface that depends on x. So in reality, it wasn't true what I said earlier, that in the phase, we are inner producting x with this sigma x. However, the phase has a first order Taylor expansion that is such an inner product. Okay. And there are higher order terms that come from differentiating with respect to x in higher order. And those actually look more and more like zero as r goes to infinity. Okay, so to have potentially similar bounds as for the extension operator, we want these variable surfaces to be hypersurfaces of non-vanishing Gaussian curvature. And here's how we say they should be hypersurfaces. We take all the normals, all the tangents, and we ask that they're linearly independent. Okay, so this ensures that the variable surfaces are hypersurfaces. And then we want them to also have non-vanishing Gaussian curvature. So we take the arbitrary normal and we look at every such variable surface locally around that normal, and we ask that the Hessian is non-zero. Okay, so these are H1 and H2. Don't think too much about them. Just remember they ensure that these variable surfaces are hypersurfaces of non-vanishing Gaussian curvature. And Hermander suggested that with these two assumptions, the phase looks enough like the phase of the extension operator so that the same bounds should hold. And that was when a question asked in the 70s, and in the 80s, Stein showed something very promising, that that's almost true. So he showed that we have LP bounds for P very close to n over n minus 1 times 2. But then in the 90s, Bourgain showed that this is sharp. So for the Hermander problem, there's always some phase function that for which this exponent can't be improved. You can't get any closer to the one Hermander suggested. And in fact, in 2011, Bourgain and Guth showed that you can do a bit better in even dimensions, but still that is sharp again. Okay, so there's that. The answer to Hermander's question is no. But if you study the examples of Bourgain and Guth, you notice that the operator they gave, the Hermander operator they gave, that corresponds to sharp exponents, that is an operator where the variable surfaces have minimal signature. So maybe the signature has a role to play here. And if you increase the signature so that the surfaces look more and more like paraboloids, then maybe you can get closer to the Hermander suggested bound. So that's what we do here. We give sharp bounds according to what the signature is. So for the signature slightly bigger too, we get a bit closer. This is a sharp bound that we get. We get an enlarged range of exponents for a larger signature, etc. And we stop when the signature is maximal because that's something we treated in 2017 with Larry Guth. Okay, so this is the whole picture. The closest you can get to Hermonder's bound is this. It's when the surfaces, the variable surfaces, look very much like paraboloids, so maximal signature case. And as the signature decreases and the surfaces start looking more and more like saddles, you get further and further away from Hermonder's suggested bound. Okay, so the exact theorem is the following. And it is sharp here, the exponents are sharp. If we get any phase function satisfying the two Hermonder conditions for non-vanishing Gaussian curvature and hypersurfaces, then we have that these surfaces have a certain signature. So these come by looking at the positive eigenvalues minus the negative eigenvalues of this matrix here, the Hessian, at any point. And we get sharp bounds for the Hermonder operator according to what the signature is. As the signature increases, we get lower and lower. We get better and better bounds. And these are sharp. The already known cases were the minimal signature case, again by Stein and Borgman and Guth, and the maximal signature case, which we did back in 2017. Everything else is new. And clearly this problem has a lot to do with the signature, unlike the restriction problem. So let's see how the Hermonder operator is actually very different to the extension one, why this happens. For the extension operator, let's just start with a given function that has some big mass on the unit ball. Okay, it's spread out, its domain is spread out. Now the extension operator will take this mass and it will spread it out a lot along tubes. And the reason this mass is spread out is that the tubes will point in directions normal to the caps above. In the case of the Hermonder operator, if we use the same f, we said that instead of straight tubes that carry the waves, we have curved tubes. That's the difference. But now, because of this curvature of the tubes, it's possible that the tubes are actually clustering on a very low dimensional surface. So this is possible, packing along a low dimensional surface, irrespective of the signature. So this means that the mass, that's carried by the waves, can come and be piled up on a very, very thin space mainly, which means that the mass of the extension operator of the Hermonder operator can be very big in this neighborhood of this surface. And because of these high peaks that it will have, it makes some nice bounds impossible. Okay, the extension operator bounds are always better than the general Hermonder bounds because this happens irrespective of the signature. Now, if the signature is 0, that's the worst case scenario. So if we have saddle-like surfaces, then not only can the tubes cluster like this, but actually the mass of the operator can be huge, extremely close to this variety, to this surface. And what do I mean by that, by extremely close? Well, let's look at the neighborhood of the surface that contains these tubes. The tubes have a thickness, they're quite fat actually. So this R is quite big. And theoretically, it could be that along my surface, if I look transversely, I still find a lot of mass. So the mass is sort of equidistributed around my surface. But if the signature is 0, it could be that I have a lot of cancellation at some distance from the surface and very high peaks in the middle. In fact, I could have high pileup of mass in a neighborhood of width 1 and nothing else outside. So these are even bigger peaks than before, okay? And the point is that as the signature increases, So as we move from saddles to paraboloids, essentially, this kind of scenario is more and more prevented. Okay, so this high mass concentration, closer than normal to a surface, is prevented in principle. And in some directions, we will have a nice spreading out of the mass. Okay, that's why for higher signatures, we have better bounds. And I'd like to demonstrate that, why this happens, via the extension operator even. We don't even need to go to Hermander for this. So let's take the one extreme. We are in R3 here. We have the paraboloid. That's full signature. And let's suppose that we have tubes piling up on a plane here, a vertical plane. That's the simplest possible case of piling up close to a surface. And we want to see that actually this mass of the operator will be equidistributed within some distance from the surface. And I won't have too big of a pileup extremely close to this plane V. And this will be true because of some uncertainty principle. So mainly I need to find what caps give these tubes. And I need to see how those are localized. Okay. So this is the question, what caps do these tubes come from? All right, so let's see, let's take a cap and let's see what kind of directions it can give rise to. So the direction is the one on top, the normal of the cap right on top. And we know that in the case of the paraboloid, the normal is given by the same coordinates as the cap, comma -1. So mainly we're looking at all the directions inside V. They are of this form, ω1, ω2, comma -1. And we are looking for the corresponding ω1, ω2 down here on the left. And those are very easy to find. So the ω1, ω2, -1 along this plane will form a line. And I'm just looking at the corresponding ω1, ω2, which just form a line through 0 because my plane is vertical. And the caps I'm looking for are just on top of this line. So they live on a slice of on a vertical slice of the paraboloid, which is actually the same slice as V is. Okay, so all these caps live on V, in fact. And because of this localization of the frequencies, I have, by some uncertainty principle, that the mass of the operator of the Fourier transform is equidistributed in directions transverse to V. And that's why things work for the paraboloid very well. And okay, I did take a vertical plane here, but even if I had taken a tilted plane like this, so let's say 45 degrees angle with the previous one, still, I look at all the directions on this plane, they form a line. Now the ω1, ω2s that I'm looking for, again, form a line in the domain of F, and the caps I'm looking for live above, right above that line, again on a slice, vertical slice this time, of the paraboloid. I have a co-distribution transversely to this vertical slice. That's not exactly what I wanted. I wanted a co-distribution vertically to V. However, these planes are not too far apart, okay? They are at most 45 degrees angle from each other. So if you have a equidistribution in these directions, you also have in these ones. And this generalizes to all surfaces, all varieties mainly, and that helps. The other extreme is the saddle. And you can see that this fails completely here. So let's take a specific V here, that is the ZY plane. And let's say that we have tubes coming from the extension operator that cluster on that plane. Where do these tubes come from this time? So let's see how a cap gives rise to a normal. The cap on top has this normal that, however, has a different formula from before. The coordinates of the cap are flipped. Okay. So if I look at all the directions inside V, again, I have that they form a line in V. However, the caps that these directions come from are have reflected coordinates. And this time they form the x-axis. Okay, so while the directions are parallel to the y-axis, the caps live along the x-axis. So the caps on the saddle are the ones right on top of that, just like before. That's still the x-axis here. The saddle contains the x-axis, and they have equidistribution transversely to the x-axis. And that's a problem here. The equidistribution is in the wrong direction. It's not transverse to V, it's parallel to V. Okay. And this is why for the Harmonic operator, when it comes to low signature, we have a problem. This equidistribution that I liked, that said the mass doesn't pile up too much close to V, it fails. It can fail. Now, if we have an intermediate signature situation, so this is a general hyperbolic paraboloid, where I took this function I'm graphing here, and I split it in a hyperbolic part, which contributes 0 to the signature, and an elliptic part that contributes the whole signature. Now something intermediate happens here, and mainly within some directions, transverse to V, I will have equidistribution, and within others, I will not. So let's see why this happens. Let's take again all the directions inside V. They form a line, this gray line as before. But as we said, the caps that these directions come from live somewhere else, in another subspace. So in the orange part, the coordinates are flipped from the gray subspace. But in the green part, the coordinates are the same as in the green subspace, as in the gray subspace. Okay, so while before for the saddle is where this had intersection 0, the two spaces, now they don't. They have a big component that's similar, thanks to the high signature, and that helps. So let's see, just like before, the caps along this surface are right above my red subspace. So I have equidistribution vertically from this vertical plane. Okay, so I have equidistribution horizontally, transversely to C. These are the good directions in which I have equidistribution of the Fourier transform. That's not quite what I wanted. I wanted instead equidistribution along these gray directions, so transversely to the gray space. But as we said, because the gray and the red space share large common parts, some of the gray directions will be good. Okay, and let's see, we actually have equidistribution in the good directions that are contained in the gray ones. In other words, in this orthogonal complement here. And we can see that if the signature is high and V is quite low dimensional, and that's really the enemy here, clustering on low dimensional spaces, this is a non-trivial space, unlike the saddle situation. How do we see this? Okay, it's not, you need to take specific numbers to see it, but in any case, the sum of these two spaces, the gray and the red one, can't be the whole horizontal plane in principle, because they are sharing this big component. So when you add the two spaces up and you add that common component, you don't get any doubling mainly. Okay, so this makes the sum pretty small and the orthogonal complement pretty large. Okay. So that's the main way signature plays a role here. Because, yeah, it gives this high common component between the two spaces. There is another place where the signature plays a role, and that has to do with multilinear restriction. So what is that about? Just for the extension operator, we want to understand the Fourier transform of a specific function, and it's nice to split this function into smaller bits. And multilinear restriction is about understanding the extension operator coming from transverse caps. So when all these normals here in this picture are linearly independent, essentially. So we have a conjecture that says that if the surface has signature sigma, then we have some L2 to LP estimates, multilinear estimates. For P, so for low P, but how low it gets depends on the signature and the level of multilinearity, on how many functions, the K functions we have here. So the lowest possible P's are these ones. So you see that for low levels of multilinearity, we actually have this result. It's the one by Stein. Maybe you remember it from earlier. Stein proved it for the linear problem, and then you just use Hölder's inequality to get it for the multilinear problem. For many functions, so high levels of multilinearity, we get this from Bennett, Carberry, and Tao. And for intermediate levels of multilinearity, this is unknown. This is a conjecture that's a natural generalization of one by John Bennett. And that was for maximal signature. So here, because we need such multilinear estimates to get our linear ones, because we like this chopping up in smaller parts, we prove sort of multilinear restriction for these intermediate levels of multilinearity, but not exactly, because our left-hand side, the one we're using, is just a bit weaker. So we use the same exponents, but weaker left-hand side. Still good enough to give us what we want. And I'd like to just say that I find it interesting that for this L2 based theory, so when the right-hand side we have L2 norms and not LP norms, we get sharp bounds simply for the extension operator. You don't even need to go to Hermander. So signature does play a role in the L2 based multilinear theory, while it shouldn't play a role in the general restriction theory. Anyway, so how do we use this result? There is a general process where you start from multilinear estimates, you put them into a process developed by Bourgain and Guth, and that process spits out linear estimates. So mainly understanding what happens from different parts, from different transverse caps, will get you to what happens for the whole function. Now, this, as I said, comes from taking a whole function and chopping it up in smaller parts. And yes, these transverse situations will be dealt with multilinear estimates. However, we have also the situations where the caps are not transverse, like this one. So you see all the normals here will live on the same plane in this picture. So they're not linearly independent. Okay, so these are the cases where the function is restricted on a slice of the surface. And we need to deal with such things. So we need to understand mainly the extension operator of the whole function, of the whole red function, from its little bits. And this is done using decoupling. So that's what decoupling does. But something about it is that it's more efficient the more curvature you have. So think of the slice, it's high dimensional, and it could have some degenerate bits. So in some directions, the curvatures could be 0. Okay, and that's bad. It gives worse decoupling estimates. However, the higher the signature is, the more curvature we have. Okay. And you can think of this, for example, with a saddle. The saddle has 0 signature, and it contains lines. Okay, so there are slices of the saddle that are lines, and along these lines, you can have a lot of caps, but you can't have a very nice decoupling estimate. However, if you have higher signature, if you get a slice, you get a more curved slice than before, and you get better decoupling estimates. And that's it. Okay, I think I was done extremely fast. I'm sorry, I've never given this talk before, and I thought it would take much longer. I hope I wasn't rushing too much. Sorry.
We thank you again very much.
Thank you. Thanks for inviting me. Thank you.
Thank you very much.